Hello friends, my name is Morad Nwaili. In this video I'll try to explain the solution of the problem mirror reflection from leetcode. This solution is not mine. I can say I was completely stuck on this problem. When I read the discussion here, I found this solution from of this guy. It's very smart solution. He explained a little bit here how he find this logic. What I'm going to do here is to explain the same solution but more deeply here. Okay, let's see the problem statement here. We have a square room with mirrors on each wall, on each of the four walls here, except and we have except the southern corner, the bottom left corner. In the other corners we have receptors. On this corner, in the bottom left corner, we fired a laser. The laser meets the east wall at distance equal to q, as said here, this wall. Our job is to find the number of the receptor that the ray meets first. For example here, if p is equal to 2 and q is equal to 1, the mirror that the laser meets first is the mirror number 2, as shown in this picture here. For me, I will take this example. P is equal to 5, Q is equal to 3. The receptors here, receptor 0, 1, and 2. This is the laser. Imagine now the logic of the solution. We have to imagine now that the laser is not reflected and passes through many rooms stacked horizontally and vertically in a manner which simulates the reflection in the original room. Okay, maybe this is not obvious at the first time, but let's see how it works for this example. We extend the laser here from this point and the q equal to 3. We extend it until some points. The laser is not reflected. Imagine now the laser passes to another room. Let's show in this picture here. This is the original room. The laser will be reflected like this. But the other room it will not be reflected. It continues to pass and will hit this wall. This wall, which wall? Is it 1, 2? Is obvious is 1, 2 here. 1, 2 is 2 here or 1 here. 1 here or 2 here, or 2 here or 1 here. If you see here, if we flip this reflection here to the other room, it will coincide with this line, of course. So the receptors will flip too, using this vertical line, like you turn a page of a book here. This one became here. 0 became here, and 2 will become here. This is the next row. Then the line will pass to the other row. This is the second room. This is the third room now. This one, as you see, second reflection in this room. Yeah. Okay, let's do it quickly in the whiteboard here. Where is it? Okay, this is previous work here. Let's delete this quickly. Just yeah, I'm going to do it for 2 or 3 rooms, and for the rest it will be obvious, guys. Okay, let's delete all this quick like this. Okay, yes, good. Now the line pass through the next room here. So this one. This this reflection is this. Let's zoom to see it better. Okay. If we flip this room, this original room, this one here, if we extend the light from this room to this room and we flip the room here, this line must coincide with this line. This is the reflection of the first reflection here. Like this. So if we flip the room using this line, using this vertical line, we flip to the right, we flip horizontally to the right, we have 1 here, 0 here, and 2 will be here. Now for the next room, this is the other reflection here. We flip, so 1 here, we flip the vertically now, and 0 will be here. Okay, the reflection now will be on this on this wall, like this. I think is here. Okay. Let's do an error. No, the other side. Okay. Let's do it for the next room and we finish this. Okay. Here we put what? As you, okay, correct. We're gonna put to we flipped now. We flipped the room horizontally to the right. No, this is here. Okay, and this is here. We continue like this. We continue like this. We're gonna reach a corner. Okay, this corner here. Continue like this until reaching a corner. As you see, we have 6 reflections here. 1, 2, 3, 4, 5, 6. No, the reflection. This is the original. This is the laser. Is not a reflection. Reflection starts from here. 1, 2, 3, 4, 5, 6. Which corner number 1 as you see. The width of the stacked rooms or boxes is 5p in this example. We have 1p, 2p's, 3p's, 4p's, 5p's. Or we have 3p's, 1, 2, 3, or 5 cubes. We can divide this height by the length of this spot, cube. We have 1 here, 2, 3, 4, 5. If we compute 3 times p, 3 times 5 equal 15, 5 times q, 5 times 3 equal 15. We have the same height here. Okay? In general case, we have the stacked rooms here or boxes, n times p for the width, m times q is equal required k times p for the height, where n is the number of the rooms stacked horizontally, k the number of the rooms stacked vertically, and m is the part of the length, the number of the part of length q, number of the parts and length q. Now, if we label the rooms like in the illustration below, because we flip the rooms here, the receptors will change of the position. The positions of the receptors will change here. This one, let's call it A, this configuration A, this configuration B, this one C, this one D. We obtain, if we draw the stacked rooms using this configuration, in the first line we obtain A, B, A, B, A, B, and so on. The second line C, D, C, D, C, D, and so on. We come back to A, B, A, B, and C, D, C, D, and so on, etc., until we reach a corner here. So the end room is where the light hit a corner, so it is A, B, or C, or D. We have 4 cases here. If n is odd and k is odd too, the light ends at room A, as you see, which is the corner number 1. As you see, if A is odd here, if n is odd, with n is the number of the boxes of the room made horizontally, and K is the number of the rooms made vertically. We have here, if n is odd and k is odd, so n 1, for example, 3, 5, 7, 9, 11, etc. K is odd to 1, 3, 5, etc. We end always on A. Let's see it quickly here. I don't know if I have an example here. Okay, here A, B, A, B, A, B, C, D, C, D, C, D, A, B, A, B, A, B, C, D, C, D, C, D. This, for example, 1, 2, 3, 4, 5, 6. This is N and this is K. 1, 2, 3, 4. If, for example, if N is odd and K is odd too, for example, we will see we have A here 2, here 2, odd. Okay, we have always A. If n is even and k is odd, the light ends in room B, which color number 2. Same logic here. If n is odd and k is even, the light ends in room C, which corner 0. Same logic. If n is even and k is even, the light ends in room D, which has no corner here. So this will not be in the output for our problem here, because all the test cases guaranteed to so that the ray will meet a scepter eventually. So we have an answer here. The ultimate question now, how to find n and k. This n and this k, or this m. Because we use n and k here to check in which corner the lights end, we're gonna compute n and k. Okay. So we know that MQ is equal to KP, and the width of the horizontal stacked rooms is n times p. Let's say that x1 is equal to n times p, and x2 is equal to n times q. So we can write x1 over x2 is equal n times p over n times q, which is x1 times m over x2 times n equal to p times q. This is a simple algebra, guys. Very simple. If we dig in our memory here, personally I didn't find this. This is the definition of the lowest common multiple between p and q. The LCM of p and q. This is the definition of the LCM. If Z is equal to LCM PQ, then the definition of the LCM is Z over P, sorry, this is my French language here, Z over P is equal W1, and Z over Q is equal W2. So Z over Q over Z over P is equal W2 W1, which is P over Q is equal W2 over W1, which is x1 times m over x2 times n. We have x1, this definition of the LCM of P and Q, x1 times m over x2 times n equal P over Q. We can write it, we can divide this one. Let's write it here. Okay, very quickly. We have x1 times n over x2 times n is equal p over q. We can divide this by, for example, use x1 here. We divide this by x1, so we have to divide this one by x1. The equality is still will remain here because we divide with by the same quantity. We get this is we get here x1 times m over x1 over x2 times n over x1 is equal to p over q. This is equal to m over x2 n time over x1 is equal to p over q. You can wonder how this is true. We can say, let's say in general here, if a over p is over b is equal to c over d, we can say that a over x, for example, over b over x is equal c over d, because a over x, this one become this, a over x times x over p over b, sorry, is equal to c d, c over d. We can it became the original one. A over p is equal c over d. So we can say this. Okay. We can divide it by x2. Choose here x1 or x2 or any other number here. We choose x1, x2 for a purpose, of course. If you divide by x1, we get m over x2 times n over x1 is equal to p over q, or x1 times m over x2 over n is equal to p over q. This is lead us to z over p is equal to x2 times n over x1, or z over q is equal to m. Let's take this one, this first one here. Let's delete this. As we have seen, this is the definition of the LCM. LCM PQ. LCM PQ. Let's recall it here. P over Q is equal to W2 Wn. This is comes from here. Z over P is equal to W1, and Z over Q is equal to W2. Okay, which is the same equality here. So we can say that Z over P is equal to W1, which is this one, x2 times n over x1, or Z over Q is equal W2, which is n over Q here is equal to m. This is lead us to Z is equal to mq, the LCM. Z is the LCM of P and Q. And Z over P is equal to X2 is M Q, this X2 times N, this one. And X1 is N times P. We can eliminate N here. So Z over P is equal to MQ over P. So we can eliminate P. So Z is equal to MQ. We have the same quantity. This is for the first one. The second one, this one, x1 times m over x2 over x2 times n over x2 is equal P over Q, leads us to the same, if we do the same logic here, x1 times m over x2 over n is equal P times Q. This leads us to this, that Z over P is equal to n here, and Z over Q is equal to x1 times m over x2. This leads us that Z is equal to MP, and this one leads us to Z is equal to MP. We have two quantities of Z, M times Q or M times P. Which one? Remember that we want to compute the lowest common multiple, the LCM. If we come back to the first image here, we have here a rectangle, triangle. So the tangent of theta is equal to MQ over MP, M times Q over N times P. We know that theta is between 0 and 44. Why? Because in the problem we say that the laser here always hit this wall. So this wall, the maximum is here we have 45 degrees. Let's come back quickly to this image. Here, okay, this is theta, the angle. This is here. This is where the wall where the laser will be fired. The first wall met by the laser, if fired from here. So this angle, it can't be over this angle. It be always below here on this side. So this side is below 45 degrees. If theta is 45 degrees, below 45 degrees, though, the tangent of theta is between 0 and 1. That leads us that MQ is always lower than NMP. N times Q is lower than N times P. So we conclude that Z, which is the LCM of P and Q, is equal to MQ. We know that from the first here, Kp is equal to MQ, which is Z. K times P is equal to Z, so K is equal to Z times P. How to compute N now? We have to use the XY coordinates of the 3 points of the extended line here. The first point is at 0, 0. The second point here is PQ. This is P and this is Q. We're going to use these 2 points to compute the slope of this line. Very quickly, the slope of this line is A, is 0 is equal to A times 0 plus B, and the Q is equal to A times P plus B. B is equal to 0 and A is equal to Q times over P. We have the point MP Z, this point here, MP X is MP, N times P, and Y is Z, MQ. So we can compute N. Donc, Z is equal to A times N times P, which is Z is equal to Q times N times P over P, N is equal to Z times over Q. Z N is equal to Z over Q. As we have seen earlier, we can specify the function that will compute the which corner will hit the laser. 0 if n is even, as we have said, and the k is odd. 1 if n is even and k is even to. 2 if n is odd, is even, sorry here. If n is odd, 0 if n is odd and k is even. 1 if n is odd and k is odd. 2 if n is even and k is odd. This case is not in the problem here. -1 otherwise. We can reduce this to. Let's check it here very quickly. Okay. When we return to, if we have this case we have only one time. For the other case, n is odd, n is odd. So if n is, we can say if n is even, return 2. And n is z over q. So if z, sorry, one more time, my French English, my French language comes over here. Return 2 if z over q, z over q mod 2 is equal to 0. For this, this is for 2. Or we have here the same condition, but here is different. If k mod 2 will return 0 or 1. 2 is returned by this condition. 0 and 1 can be returned by this formula. If k mod 2 is equal to 0, we will return 0. So we return the rest of k modulo 2. If it's equal to 1, return 1. So we can, and the k is as we have seen, z over p. Okay, z over p for k. So we can use this specification now. 2, return 2 if z over q mod 2 is equal to 0, or return z over p mod 2, the result of z over p mod 2. Otherwise, with z is the lowest common multiple of p and q. The code here, let's see it here is better. Okay, as you see, we compute the lowest common multiple between p and q. Use the specification of the formula as we have seen. Z over q mod 2 is if equal to 0, return 2, then return the result of z over p mod 2. The LCM is computed by this formula. If you don't remember this, you can return to Wikipedia or any other resource to review or to remember how to compute the LCM. It's A times B over the greatest common divisor between A and B. The greatest common divisor is computed by this one, by the Euclidean algorithm. This one. We compute always B, the greatest common divisor between B and A mod B if A mod B is different to 0. Otherwise, return B. Let's submit this and see what happened. As we see, it's accepted. Sorry guys if I stuck in any point. Sorry for my stuttering. As you see, I stutter a little bit. Thank you for watching. and see you on a next video.